Welcome! In this lesson, we'll explore problem number 561, array partition. This problem challenges us to maximize the sum of the minimums of pairs in an array. We'll break it down step by step, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, you are given an integer array called nums that contains 2n elements, where n is a positive integer. The task is to partition this array into n pairs, with each pair containing 2 integers. The goal is to maximize the sum of the smaller numbers from each pair. Essentially, for every pair you form, you take the minimum value, and the sum of these minimum values across all pairs needs to be as large as possible. The input is an array nums with a length of 2n, where n can range from 1 to 10,000, and each element in the array falls between -10,000 and 10,000. The output will be a single integer representing this maximum sum. To help clarify, let's look at some examples. Here's the first example. If the input array is nums equals 1, 4, 3, 2, the output is 4. To achieve this, you can form the pairs 1, 2, and 3, 4. In the first pair, the minimum value is 1, and in the second pair, the minimum value is 3. Adding these minimums gives 1 plus 3 equals 4, which is the maximum sum possible for this array. This demonstrates how the choice of pairs impacts the result. Let's explore another example to solidify the concept. Now consider the input array nums equals 6, 2, 6, 5, 1, 2. The output in this case is 9. One way to form the pairs is 1, 2, 2, 5, and 6, 6. For these pairs, the minimum values are 1, 2, and 6 respectively, and their sum is 1 plus 2 plus 6 equals 9. This is the highest sum of minimums we can achieve with this array. The examples highlight the importance of strategically forming pairs to maximize the sum, which we'll further explore using the problem's constraints and edge cases. There are a few important constraints and edge cases to consider. First, the length of the array is always even, between 2 and 20,000 elements. Each value in the array is guaranteed to fall between -10,000 and 10,000, and the array can always be partitioned into valid pairs. For edge cases, if the array has only 2 elements, like nums equals a, b, the result will simply be min, a, b. If all the elements in the array are equal, such as nums equals 2, 2, 2, 2, the result will be the sum of n identical values. When the array contains only negative numbers, for example nums equals -1, -2, -3, -4, the algorithm still works by pairing and summing the smallest values correctly. Similarly, if the array has mixed positive and negative values, like nums equals -7, -3, 5, 9, the pairs -7, -3, and 5, 9 yield a sum of -7 plus 5 equals -2. These cases demonstrate the robustness of the solution and highlight the need for an efficient approach. The optimal way to solve this problem involves sorting the array and then summing the appropriate elements. First, sort the array in ascending order. This ensures that smaller numbers are grouped together, which helps maximize the sum of the minimums. Next, form pairs by taking every 2 adjacent elements in the sorted array. For example, if the sorted array is A, B, C, D, the pairs would be A, B, and C, D. Finally, sum up the smaller values, which will always be the first element of each pair in the sorted array. Sorting the array takes O, n log n, time, and summing the elements after sorting takes O, n, time, making the overall time complexity O, n log n. The space complexity is O, n, typically required for sorting. This approach ensures that the solution is both efficient and easy to implement. To solve this problem, let's start by considering the brute force approach. The idea here is to generate all possible pairings of the array into n pairs, calculate the sum of the minimum values in each pairing, and then return the maximum possible sum. This ensures that we explore every possible combination to find the optimal solution. Now, one key observation is that to maximize the sum of these minimums, smaller numbers should ideally be grouped together. This pairing strategy minimizes the dilution of larger values, allowing us to maximize contributions from other pairs. However, while this approach guarantees correctness, it's computationally infeasible for larger arrays due to its factorial growth. Generating all combinations results in a time complexity of O, 2n, which quickly becomes impractical as the size of the array increases. This leads us to explore a more efficient alternative. Instead of brute force, we can use an optimized approach that leverages sorting. Here's how it works. First, sort the array in ascending order. Then, pair adjacent elements so the pairs would look like nums 0, nums 1, nums 2, nums 3, and so on. To calculate the result, simply sum the first element of each pair, which corresponds to nums 0, nums 2, nums 4, and so forth. Now, why does this work? Sorting ensures that the smallest values are grouped together, which minimizes the loss and the minimum contributions of each pair. This greedy approach is both intuitive and efficient, guaranteeing an optimal solution without needing to exhaustively search through all combinations. In terms of complexity, sorting the array takes O, n log n, and summing the selected elements takes O, n. Overall, this approach runs in O, n log n, making it vastly more efficient than the brute force method. Sorting emerges as the preferred strategy here because it is both efficient and simple to implement. With a time complexity of O, n log n, it scales well to larger inputs and directly leverages the structure of the problem to form optimal pairs. By pairing adjacent elements after sorting, we avoid unnecessary computations while still ensuring correctness. Compared to the brute force method, sorting is far more practical. While brute force guarantees correctness by exploring all possibilities, it is computationally prohibitive for larger arrays. On the other hand, the sorting-based approach strikes a balance between correctness and efficiency. It does rely on the insight that sorting suffices for optimal pairing, which might not be immediately obvious to everyone, but the trade-off in efficiency makes it worthwhile. In summary, the sorting-based solution is the most practical and efficient approach, allowing us to solve the problem within the given constraints, such as nums.length being up to 10,000. To solve the array partition problem, the goal is to maximize the sum of the minimum values from n pairs formed from the input array. The first step involves sorting the array in ascending order. This is crucial because pairing smaller numbers together results in a smaller minimum, which is not ideal. Instead, to maximize the minimum values, we pair the smallest available number with the next smallest number, which are consecutive elements in the sorted array. For example, if the input array is 6, 2, 8, 4, sorting it gives 2, 4, 6, 8. Now, the next step is to form pairs by grouping consecutive elements together. Specifically, we take elements at even indices and pair them with their consecutive elements. This ensures that the first number of each pair, which is always at an even index, will represent the minimum value for that pair. This approach simplifies the pairing process while ensuring optimal results. In the sorted array 2, 4, 6, 8, the pairs formed are 2, 4, and 6, 8. The minimum value of each pair is 2 for the first pair and 6 for the second pair. The next step is to compute the sum of these minimum values, which simply involves summing the elements at even indices in the sorted array. In this case, the sum is 2 plus 6, which equals 8. This value represents the maximum possible sum of the minimums for this input array. Finally, the computed sum is returned as the result. This step-by-step process ensures that we achieve the optimal solution efficiently and correctly. There are some key insights that make this algorithm both efficient and effective. First, sorting the array guarantees that the smallest elements are paired together, which ensures that the sum of the minimums is maximized. Without sorting, there's no guarantee that the pairs will be optimal, and additional computations would be needed to determine the best pairs. Second, the minimum value of each pair, when the array is sorted, always lies at the even indices. This eliminates the need to explicitly create pairs, as we can simply sum the elements at even indices to get the result. Finally, from a time complexity perspective, sorting the array takes O, n log n, and summing the elements at even indices takes O, n. Therefore, the overall complexity of this approach is O, n log n, which is efficient for the problem at hand. The algorithm relies on minimal data structures, making it both simple and memory efficient. The input is processed as a standard array, and sorting can be performed either in place or with additional memory, depending on the language and sorting method used. Notably, there is no need to create explicit pairs or use additional data structures to store them. Instead, the algorithm leverages the sorted order of the array and uses indices to identify the pairs implicitly. For the accumulation of the sum of minimum values, only a single variable is used. This streamlined approach minimizes memory usage while maintaining clarity and efficiency. It's important to consider edge cases to ensure the algorithm handles all possible scenarios correctly. For an empty array, no pairs can be formed, so the result is 0. If the array contains exactly 2 elements, it already forms a single pair, and the result is simply the smaller of the 2 elements. When all elements in the array are equal, the sum of the minimums is just half the total sum of the array, as every pair will have the same minimum value. Finally, the algorithm works seamlessly with negative numbers because sorting handles negative values correctly, and the logic for pairing and summing remains unchanged. These considerations make the algorithm robust and applicable to a wide range of inputs. The problem asks us to maximize the sum of the minimums of n pairs formed from the array. The optimal approach is to sort the array first and then sum up every second element starting from the first. This ensures that the smallest elements are paired, contributing their value to the sum, which maximizes the result. Explanation. 1. Sort the array. The first step is to sort the array in ascending order. Sorting ensures that the smallest elements are adjacent, making it easier to form pairs that maximize the sum of minimums. 2. Iterate over every second element. After sorting, we loop through the array with a step of 2, starting at index 0. This approach directly selects the smaller number of each pair, which is the first number in each consecutive pair after sorting. 3. Sum the minimums. Add each selected number, at index 0, 2, 4, etc., to the result variable. This guarantees that we are calculating the maximum possible sum of the minimums. 4. Return the result. Finally, return the accumulated result after the loop completes. Example. Input 6, 2, 6, 5, 1, 2. After sorting 1, 2, 2, 5, 6, 6. Select elements at indices 0, 2, and 4, 1, 2, 6. Sum 1 plus 2 plus 6 equals 9. Output 9. The algorithm runs an O, n log n, due to sorting, followed by an O, n, loop, making it efficient for larger inputs. This is the Java implementation for LeetCode problem number 561, array partition. The solution mirrors the Python logic. The array is first sorted, and then the sum of elements at even indices is calculated to obtain the result. Differences include explicit type declarations, the use of Java's arrays.sort for sorting, and the class structure required in Java. This code is concise and adheres to Java conventions. To solve this problem, we need to maximize the sum of the minimum values from pairs formed in an array of 2n integers. The optimal way to achieve this is by sorting the array first, as sorting ensures that smaller numbers are grouped together, which maximizes the contribution of the minimums. Let's look at an example. For the input array 1, 4, 3, 2, the first step is to sort it, resulting in 1, 2, 3, 4. Once sorted, we pair elements by selecting every other value, starting from the first index. This ensures that we are summing the smallest values in each pair. Specifically, at I equals 0, we add 1 to the result, and at I equals 2, we add 3. The total sum becomes 4. Therefore, the output for this example is 4. Now, let's consider another example with a larger input array, 6, 2, 6, 5, 1, 2. The first step is to sort the array, which gives 1, 2, 2, 5, 6, 6. Next, we initialize result to 0 and begin iterating through the array in steps of 2. At I equals 0, we add 1 to the result, making it 1. Then, at I equals 2, we add 2, updating the result to 3. Finally, at I equals 4, we add 6, bringing the total to 9. By ensuring that we always pick the smallest value in each pair, the sum of the minimums is maximized. The final result for this example is 9. In another example, consider the input array 9, 7, 3, 1. After sorting, the array becomes 1, 3, 7, 9. Once sorted, we initialize result to 0 and iterate through the array in steps of 2. At I equals 0, we add 1 to the result, making it 1. Then, at I equals 2, we add 7, bringing the total to 8. This demonstrates the key idea that sorting ensures smaller numbers are paired together, which guarantees the maximum sum of minimums. Additionally, by iterating every 2 steps, we include only the minimum of each pair in the result. The constraints of the problem also ensure that the total number of elements is always even, so pairing is straightforward. The output for this example is 8. Now, let's analyze the complexity of this solution. The sorting step takes n log n time, which dominates the overall time complexity. After sorting, we perform a single pass through the array with a step of 2, which runs in n. Therefore, the total time complexity is n log n. For space complexity, the sorting operation is done in place, requiring no additional space apart from the input array. As a result, the space complexity is 1. This makes the approach efficient in both time and space for solving the problem. To analyze the time complexity of our solution, we need to break it down into its 2 main steps, sorting the array and summing specific elements. First, the sort function is used to order the elements of the array. This sorting operation relies on timsort, which has a time complexity of n asterisk log n, where n represents the size of the input array. Sorting is the most computationally intensive part of this algorithm. Next, we calculate the sum of the minimum elements from each pair. This is done using a for loop that iterates through the array with a step size of 2. Since the loop runs roughly n/2 times and each iteration involves a simple addition, this step has a time complexity of n. When we combine these steps, the sorting step dominates the overall performance, resulting in an overall time complexity of n asterisk log n. Now let's discuss the space complexity of the solution. The primary factor here is the memory usage of the sorting operation and the variables involved in the algorithm. Python sort function performs in-place sorting, meaning it doesn't require additional memory proportional to the input size. However, timsort, which is used internally, does require a small, fixed amount of auxiliary space, denoted as k, where k is the size of temporary storage for merging runs. Since this value does not depend on the input size, it is considered constant. Additionally, the solution uses a few variables, such as the result variable and the loop variable I, both of which take up only 1 space. Therefore, the overall space complexity of our solution is 1, as no additional memory is allocated that scales with the size of the input. When comparing this optimized solution to a brute force approach, the advantages become clear. A naive method would involve generating all possible pairings of the array elements and calculating the sum for each pairing in order to find the maximum. This process would require n time to generate all pairings and an additional n time to calculate the sum for each set of pairings, resulting in an overall time complexity of n asterisk n. Such an approach is computationally infeasible for large inputs. On the other hand, the optimized solution leverages sorting to ensure that the elements are paired optimally, eliminating the need to explicitly generate pairings. This reduces the time complexity to n asterisk log n, which is exponentially faster than the brute force approach, and the space complexity remains 1, as no extra data structures are needed. This combination of efficiency in both time and space makes the optimized solution vastly superior. Finally, let's analyze the best, average, and worst-case scenarios for this solution. Since the algorithm's 2 main steps involve sorting and summing, the time complexity remains n asterisk log n across all cases. This is because timsort, the sorting algorithm used, guarantees a time complexity of n asterisk log n, regardless of the order of the input array. Additionally, the space complexity remains consistent at 1 in all cases since no additional memory is allocated based on the input size. For a mathematical proof of the time complexity, we can break it down step by step. Sorting contributes n asterisk log n, while summing contributes n. Combining these using big O rules, n asterisk log n dominates n, so the overall time complexity is n asterisk log n. With no memory usage scaling with input size, the space complexity remains 1, confirming the efficiency of this solution in all scenarios. When solving the array partition problem, there are a few common mistakes to watch out for. First, not sorting the array is a frequent oversight. Sorting is a key step because it ensures that the smallest elements are grouped together, which is essential for maximizing the sum of the minimums in each pair. If you skip sorting, the pairings become arbitrary, leading to suboptimal results. Another mistake is using an incorrect pairing strategy, such as greedily grouping adjacent elements without sorting. This approach doesn't account for minimizing the loss in each pair, which sorting inherently handles. Lastly, overcomplicating the solution is a trap some fall into, like attempting to generate all possible pairings with brute force. While this approach is technically correct, it's computationally expensive due to its factorial time complexity, making it impractical for larger inputs. Another frequent issue is ignoring edge cases. These include arrays with all identical elements, very small arrays like those of size 2, or arrays with a wide range of values. Overlooking these scenarios can lead to runtime errors or incorrect outputs, especially during an interview. Similarly, misunderstanding the problem statement is a critical pitfall. For instance, some might aim to maximize the sum of maximums instead of minimums, which leads to implementing the wrong solution entirely. This highlights the importance of thoroughly understanding the requirements before diving into the implementation, as clarity and problem comprehension is often just as important as the solution itself. For interviews, there are a few insights you should always highlight. Emphasize that sorting is the cornerstone of solving this problem and many of its variations. Once the array is sorted, the optimal pairing strategy becomes clear: simply sum every alternate element starting from the first. This approach ensures both correctness and efficiency, as the sorting step dominates the runtime, resulting in an overall complexity of O(n log n). Be prepared to explain trade-offs if asked about brute force, acknowledging its correctness but stressing its impracticality due to factorial complexity. Additionally, mentioning edge cases is crucial. For example, describe how your solution handles small arrays, arrays with all identical elements, or extreme values, as this demonstrates thoroughness and attention to detail. This problem also has connections to several related problems that showcase similar techniques. For instance, LeetCode 561, the array partition I problem itself, is a classic introduction to greedy algorithms. LeetCode 406, queue reconstruction by height, is another greedy problem that involves sorting and pairing strategies but applies them in a more complex context. LeetCode 135, Candy, is another great example, where the goal is to distribute values optimally based on certain constraints. Finally, LeetCode 122, Best Time to Buy and Sell Stock 2, focuses on local optimizations to achieve a globally optimal result, which is a concept that aligns closely with the pairing strategies used here. Familiarity with these related problems can deepen your understanding of greedy algorithms and their applications. When discussing alternative approaches, there are a few worth mentioning. The brute force method generates all possible pairings to calculate the sum of minimums. While this approach is correct, its factorial time complexity makes it infeasible for larger arrays, so it's more of a theoretical exercise. The most practical method is sorting followed by a greedy approach. By sorting the array and summing every alternate element starting from the first, you achieve the optimal solution with a time complexity of O(n log n). Another alternative is counting sort, which has a linear time complexity of O(n), and can outperform traditional sorting algorithms when the range of input values is small. However, its applicability is limited to scenarios where such constraints are explicitly stated. Understanding these trade-offs helps you adapt your approach based on the problem's requirements and constraints. Great job! We've covered problem number 561, array partition, and learned how sorting and greedy strategies can simplify solutions. Remember to practice similar problems and analyze constraints for optimal performance. Thanks for watching, see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!